Hi, my name is Jake Russin. I'm a graduate student at the University of California, Davis, and I study computational neuroscience and its intersection with machine learning. And this is work that was done in collaboration with my advisor, Randy O'Reilly, as well as Jason Joe and Joshua Bengio, and is about inducing systematicity in a recurrent neural network by factorizing syntax and semantics. So systematicity, for the purposes of this talk, we can define it as the ability to apply known rules to arbitrary elements. This is a ubiquitous phenomenon in human cognition, but it's particularly relevant to human language, where, for example, if I tell you some new verb flug, and that it means snap your fingers and wink your left eye, then you can generalize that to flug twice and know what flug twice should mean, just based on your knowledge of the rules of English grammar and knowledge of what twice means, and so on. And so you can apply the rules that you know about how adverbs modify verbs to generalize to this new construction, flug twice, even though you've never seen it before. And so this is important because you don't need to relearn the application of or how rules should apply to particular elements with each new element. And so you can apply those rules to completely new elements without having to relearn those rules. So it's very efficient. And this systematicity has been a long-standing issue in cognitive science, going back to Jerry Fodor in the 80s, at least, who argued that neural networks, or connectionist models, as they were called at the time, are kind of insufficient for modeling human cognition, precisely because they lack this property of systematicity. Systematicity has emerged recently, re-emerged as a topic of interest in cognitive science and in machine learning as well, due to the rise of neural networks and their massive success on all different kinds of tasks, including tasks in natural language. And in these studies, it has been shown that deep learning architectures, the ones that do well on those tasks, they often fail when you test them when you test their systematicity, or the degree to which their representations that they've learned are systematic. And so one particular task, the one that we focus on in our work, is called the scan task from Lake and Baroni in 2018. In this task, sequences of instructions have to be mapped to sequences of actions, and it includes things like, jump means the action jump. Jump left means turn left and then jump. Jump thrice means jump, 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 and so on. And so these instructions are generated from a simple finite phrase structure grammar. And so there's about 20,000 total possible instruction sequences that you can generate from this grammar. And then the actions are determined according to a deterministic interpretation. And so the interesting thing is that because this data set is synthetic, you can split the data in various ways. And I'll focus on two of the ways here. So in the first, the simple split, training and testing data are just random samples from the data set, as is usual in machine learning and statistics. And then in the add jump split, it was designed specifically to test the systematicity of these models. And I'll go into detail here. So in the add jump split, the training set consists of every instruction that does not include a particular verb, jump, and then it includes, but 10% of it is composed of that verb in its most basic form. So 10% of the data set is this simple instruction jump, means the action jump, and then you get every other instruction that doesn't include jump. So you can learn, left, twice, thrice, and so on about all of the other verbs. And then the task in the test set is to generalize what you've learned about those left, twice, and thrice, and so on about the other verbs to this verb that you've never seen in those contexts, jump. And so this is meant to be analogous to that flug example I gave in the introduction, because the model knows what jump means but it has never seen it in any other context, and it has to generalize what it knows to those other contexts. And so, as I mentioned, these recurrent models, these standard recurrent models, which do so well on all kinds of natural language processing tasks, they often fail to generalize, and they generalize systematically. So these standard recurrent networks people have tested, they get about 100% on the simple split, which of course is the usual case for machine learning, where it's randomly split. And then it only gets about 1% to 13% on the add jump split, where 1% was in the original study and 13% was some follow-ups testing some more sophisticated models, such as ones with an attention mechanism. And so these models, there's a huge drop in performance when you go from the simple split to the add jump split. However, humans tend to perform well on an analogous task. So a task that was specifically designed to be analogous to this add jump split, humans perform quite well, as was shown by Russin and Baroni in 2019. And so something seems to be missing from these deep learning models, as shown by their lack of systematic generalization compared to humans. And so I think it's instructive to think about the symbolic approach, which is perhaps the paradigmatic case of systematicity, where if you're dealing with variables, which are by definition arbitrary content, then you can generalize systematically by default. So for example, if I wrote a symbolic program that was do twice x, it takes an argument x and just does it twice, then this program can generalize no matter what I put in there for x, as long as it's the right data type and so on. But it can generalize, even though it's never seen, some particular values of x, it can still perform this function just as well. And so I think if we were to get a kind of abstract principle from this, it might be that when you separate representational content from the structure or the manipulation of that content, then you get this kind of natural systematicity, because if the manipulation doesn't depend on the particular value of the content, then you kind of get that generalization for free. The problems with the symbolic approach, on the other hand, are of course that symbols are rigid, they're hard to learn with, they require a lot of hand coding on the part of the engineer. And these are things that the rise of deep learning and machine learning in general has shown us are kind of serious problems if we care about robust artificial intelligence. And the other problem is, it's unclear, although there has been some work on this, it's unclear how symbolic structures can emerge in a strictly neural system, like the human brain. And so our idea was to kind of try to capture this intuition about separating structure from content in the context of one of these powerful recurrent neural networks. And so in this case, with the scan task, we might call the structure syntax, or the grammar governing the instruction sequences, and the semantics, what the individual words mean. So what we did was to modify an existing neural architecture, which is the model of Bahdanau et al. 2015, which is a recurrent neural network designed for translation that it has an attention mechanism. And we modify it to have this separation between what we're calling syntax and what we're calling semantics, where the syntax is given access to the word order, so it can learn things like the dependencies between words, like how adverbs modify verbs and so on, and it governs the attention, whereas the semantics is not given this access to word order, but it must learn how to actually translate those words into their corresponding actions. So it's kind of the meanings of the words in terms of what actions correspond to them. And I'll go into detail in a minute. But first, for the sake of comparison, we can diagram the model of Bahdanau et al. 2015 like so. So it's an encoder and a decoder architecture where the encoder processes the input sequence with a recurrent network called a bidirectional LSTM. And then that will produce one vector for each word, which does have information about all the other words in the sequence since it's recurrent. And those encodings are passed to the decoder and used in two different ways. In the first way, it's used to determine an attention distribution, which is just a probability distribution over the input sequence at each time step. And then in the other way, the tokens that are attended to are used to produce the action at that time step. And so the encodings are produced by the bidirectional LSTM, and then those are used to determine the attention to find which words, which particular encoding is relevant to the current time step of the action. And then again, those encodings are used to produce, after an output layer, the actual actions that should correspond to that time step. So in our model, we just made a simple modification, which was to introduce the separation between the syntax, what we call the syntax stream, shown in blue, and the semantic stream, shown in red, where the syntax stream has a very similar bidirectional LSTM setup. So that's a recurrent network that processes each of the words in the sequence, produces an encoding for each of those words, and then those are used for the attention mechanism, whereas the semantic stream just processes each word individually, and so it just generates an embedding vector for each word, and those will not have any information about any of the other words in the sequence. And then the attention will choose which of those word embeddings to attend to in order to produce the action at each time step. And so I should mention that we didn't hand code syntax or grammar, or we didn't supervise the syntax stream with parts of speech or anything like that. So we just want the model to learn what syntax is on its own, and we impose this separation in hopes that what will be learned in this stream will be something like syntax, and what will be learned in this stream will be something like semantics, and that by separating these out, this will encourage systematic generalization on the adjunct split of the scan task. And so here are the results. Our model, which is called syntactic attention here, gets about 78.4% accuracy, mean accuracy, on the add-jump split, which is much better than the previous recurrent models, which got at most 12.5% accuracy. And I should say also that this is the median, and that, this is the mean, and the median was actually much higher because the results were very skewed. And it does even better than a convolutional neural network, which was shown to do better than the recurrent models on this adjunct split, but does not do quite as well as the model of Li et al. 2019, which is almost perfect on the adjunct split. But this model was, as ours was designed specifically for the scan task and uses a quite similar principle. So in summary, we experimented with an inductive bias, which was to factorize or separate what we call syntax, or really the attention mechanism, from what we're calling semantics, or the individual meanings in terms of the actions of each of the input words. And this inductive bias improved the systematic generalization of an existing architecture from Bahdanau et al. 2015 on the adjunct split of the scan task. And it did so without hand coding any explicitly symbolic structures, and also without supervising on, for example, parts of speech or anything like that. Thanks for listening. If you're interested, please check out our paper. Thanks.